Today we are going to revisit the tangent and velocity problems. We'll start with the tangent problem. Remember that if you've got a function, the tangent problem asked for the following. If I were to take a single point on this function and say, let's call it A, I know the coordinates of where it touches the function. How am I going to figure out the slope of the tangent line? I have only one point. Remember that if you want to figure out the slope of any line, you need 2 points on the line. That's why this question is a bit of a problem. If you remember way back when, the idea was that we are going to approximate with what was called a secant line. We would take our function and choose some nearby point. So let's say this point lives at an address of x, and its height would be f of x. And instead of trying to figure out the equation of the blue line, we would replace it with the green line. So we would calculate the slope of that secant line, f of x minus f of a, divided by x minus a. Because remember, this point has coordinates x and f of x, and this point has coordinates a and f of a. Now, the green line is not the blue line, but the idea is that as we move the point closer to A, we get a better and better approximation. And so as x approaches A, we assume that the slope of the secant line will get closer to the slope of the tangent line. And that means we define the slope of the tangent line to be the limit as x approaches A of f of x minus f of a divided by x minus a. Now, we are also going to come up with an alternate version of this formula. There's your function. There's the point A. There's the point f of a. And again, we are interested in what is the slope of the tangent line here. We're going to try to approximate it by using another nearby point and then drawing a line there. Rather than talk about x's and a's, we are going to talk about the separation between the points. So if there's a separation of h, then another way to write x would be a plus the little bit more h. So then that slope formula becomes limit f of x. Well, instead of x, I'll put an a plus h, and we had the f of a from before. So that goes in there. In the bottom, we had an x, subtract an a. We want the separation to go to 0 because as x gets closer to a, the separation goes to 0. So then rather than writing this as a limit with an x, we are going to write this as a limit with an h. So then an alternate form would be the limit as h, the separation goes to 0, of f of a plus h minus f of a, all divided by h, because I'm hoping you can see that those will cancel out. And I'll write the one from before. Both of these things are equivalent. They're just two different ways of interpreting it. One is with the separation, one is just 2 points moving closer together. These represent the slope of the tangent line to the function f at x equals a. This calculation is so important that we give it a fancy name. This thing, m, give it a new symbol. We'll say f prime at a. This will be called the derivative of the function f at the point x equals a. Now, the root word of derivative is derive, and it tries to imply that something is coming from the function. So we are going to find the slope of the tangent line to the function y equals x cubed at the point x equals -1. So if we wanted to think of it in terms of a picture, a cubic function looks something like this, and the point -1 lives around here, has a height of -1 as well. So the tangent line looks something like that. The equation of any line, you could write it in this form, y minus y1 equals x minus x1. This is the one that calculus likes the most because you always know the coordinates of one of the points on the line. So in this case, x1 would be -1 and y1 would be -1. So the equation of the line would be y minus -1 is mx minus -1. So another way to put it would be y plus 1 is m into x plus 1. Now, of course, the hard part is, what is the slope? This is the are you paying attention moment. So we use the derivative. F of x is equal to x cubed. The slope would be the derivative at the point -1. And that means we are going to use one of the two versions above. I'm going to pick the one with x's and a's. I'll show you the other one in the next video. So in this case, a would be -1. I will plug in the function. The function is x cubed. Subtract the value of the function at -1 divided by x plus 1. So this would end up giving me the limit as x gets closer to -1 of x cubed plus 1 over x plus 1. And so ultimately what we've got is what I would like to call a strange limit. Now, I've always told you that the first thing you should do when you encounter a strange limit is to sneak a peek. And it will turn out that when we deal with derivatives, you're always going to see a 0 over 0. And that means no limit laws. There's a 0 in the bottom. And we have to do some algebra to rewrite things so that the 0 over 0 vanishes. And the proper algebra in this case is likely a formula that you've forgotten. X cubed plus 1 you could think of as x cubed plus 1 cubed is what we call a sum of cubes. And there's a way to factor it. X plus 1, x squared minus x plus 1. Now, if you don't know that or you can't remember, go Google sum of cubes and remind yourself what it is. If you use this factorization formula, you will see the 0 over 0 popping out. The 0 over 0 is this x plus 1. And when we clean that up, we are left with x squared minus x plus 1. And when we sneak a peek now, this is just going to give me a 3 over 1. So I can use the limit laws. So I'll get a limit as x approaches -1 of x all squared, subtract a limit as x approaches -1 of x, plus a limit as x approaches -1 of 1. And so this is going to very nicely work out to -1 squared, subtract -1 plus 1, which is a 3. And so the equation of the tangent line is then y plus 1 is 3 into x plus 1. So we have been successful in figuring out the slope of the tangent line using this derivative formula. Now, one last note here when we're talking about the tangent line. If we were to take our function and if we were to zoom in at the point x equals a. So if I were to take a function and if it has a tangent line at x equals a, when I zoom in to that function, when I start looking closer and closer at that function at the point, what you're going to notice is that the closer I zoom in, the less and less I notice the curviness of that graph. So if I zoom in more and more and more, you will not be able to tell the difference between the function and the tangent line. So if a function has a tangent, the function looks linear. So we say that f is locally linear if it has a slope. And so another term that we say is that f is differentiable at x equals a. And that means that its derivative exists. If a function has a tangent line, that means it has a derivative. And if it has a derivative, you can figure out a slope. And we say the function is differentiable at that point. And then sometimes we get lazy and we say that this is the slope of the function, not just its tangent line, but the slope of the function at x equals a.